Hello everyone. This is a video lecture about the discretization of ODEs. Basically, we have a problem of the form y prime of t equals f of t, y of t, and y of 0 equals u0 with f function from R plus Cartesian product R to R unknown function u0 a real number known, and y a function from the positive real numbers to the real numbers unknown. Our goal is to find a good approximation for y with a computer. How do we do this? The first step, obviously, because computers can't handle continuous functions, is to pick a finite time step. So we take tau. Really, it's a positive rational, because if we're representing it in a computer, we can't actually represent an irrational number with an infinity of digits after the decimal. So we'll take a positive rational number, which will be our time step. Now, the smaller the better, for reasons which we'll see later. And this allows us to transform time from a continuous quantity to a discrete one by saying that basically, instead of just time being a positive real number, we say that t0 equals 0, t1 equals tau, t2 equals 2 tau, and for the given n, tn equals n times tau. Now that we've discretized time, so quick notation note, we've got tn equals n times tau. We're also going to just define yn is y of tn. And y prime n equals y prime of tn. In both cases, this would be equal to y of n times tau and y prime of n times tau. Right, to approximate y prime, we use the finite difference. Y prime of tn equals yn plus 1 minus yn over tau. This is basically, if you remember the definition of the derivative, so maybe I'll put the approximation instead of equals, but the definition of the derivative is, y prime of t equals limit is tau goes to 0 of y of t plus tau minus y of t over tau. Once again, because we're dealing with a computer, it has to be a bunch of finite finite rational numbers. You can't run around using actual infinite stuff, so we drop the limit, and that's what we use. So now we're going to look at basic step methods for approximation. So these are all just kind of the variations of, okay, if we approximate y prime of t with y of n plus 1 minus y of n over tau, that gives us naturally n plus 1 minus y of n over tau equals f of t, y of t. Which value of t do we pick? Well, if we pick here tn, then we get the first scheme, which will be called forward Euler. y of n plus 1 minus yn over tau equals f of tn yn. Now, this one you'll note is pretty easy to rewrite as y of n plus 1 equals tau f of tn yn plus yn. It gives us an explicit solution for yn, and because we start with y0, we can just calculate iteratively y1 equals tau, f of 0 uo, which is our value of y0, plus uo. That gives us y1, and then we can do y2 equals tau f of, well, t1, which is equal to just tau. Y1 plus y1, dot, 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 etc. The next scheme is we decide that this value, we're going to pick at a time, n plus 1. So we get 2. Backwards, this is the second scheme, it's called backward Euler. And it's very similar to the first scheme, yn plus 1 minus yn over tau equals this time f of tn plus 1, yn plus 1. Now, unlike the previous scheme, this one was explicit, because it gave us an explicit formula for calculating yn plus 1, given yn. This we don't have here. If you, how do I put this? If you kind of try to isolate this y, and you'll find that there's still this y in here. That's on a different side of the equation. So in practice, to actually solve it, you'd have to solve the zeros of the function that x associates f of tn plus 1, yn plus 1 is times tau plus yn. Oh no, x, the yn plus 1 should be an x, sorry. Where's my eraser? And on this day, Ariel learned a very important lesson. The importance of organization. X minus x. Then you'd have to find the x's such that this equation is 0, and that will give you your values of yn plus 1. This means that this is an implicit scheme, because it doesn't give us an explicit value for calculating yn plus 1. We have to do a computational step that requires, well, an extra computation at least. So that means that ceteris paribus, if you're picking between these two schemes, pick the explicit one. Although in practice, there's some moments where this scheme will give you more accurate approximations than this one, depending on what function you're trying to approximate. So that's forward and backwards Euler. The third basic scheme, which is also implicit, it's called Crank-Nicholson, and it's a bit of a mix of the two. So Crank-Nicholson, and it just says yn plus 1 minus yn over tau equals the average, so 1/2 of f of tn plus 1 yn plus 1 plus f of tn yn. So it's a bit of a mix of the two, also implicit. Okay. General formula for a one-step method. Is yn plus 1 equals yn plus tau, phi of tau Tn yn where via tau continuous function can depend on tau. Right. Now we're interested in how well does this work. So we want to measure errors. Global error is simply defined as y of tn minus yn. Nope. This is equal to en. Now, here we're using a different kind of notation. This is the value that our approximation returned, and this would be the actual value of the function if we can calculate it somehow at time n. So this is the approximation actual value of the function. And we also have the truncation error, Tn is equal to basically the finite difference, which approximates the derivative, minus phi of tau f of Tn y of Tn. And again, this is the approximation, this is the actual value. And so it's kind of in theory, these should be equal, and the difference between them is, well, how good or bad our approximation is. A theorem, which I'm not going to prove, in certain cases, global error bounded by a function of truncation error. Convergence. Alright, just a quick discussion of convergence. Now we mentioned earlier with tau, tau smaller is better. And in general, the smaller the time step, the more precise the approximation. However, not all schemes converge equally rapidly. So basically, we say that a scheme is of order p if the error is a function of to use complexity notation, I guess, big O of tau to the p. In other words, en is a function of what this, if you want a very formal definition, it's there exists an f from what? Positive real numbers to positive real numbers, such that f is a polynomial of degree p and en less than or equal to f of tau. Or I guess for Tn, sorry. For y. So, bon, the previous schemes we've seen are all of t. If we can get some schemes that are, for example, O t to the 4, then we get stuff like you have the time step, and the scheme gets 16 times more accurate. So with O to the 4 half time step, error decreases by 16, which is good. Right, next we're going to discuss a special case of one-step methods called Runge-Kutta methods. And they have the particularity of basically, in order to increase accuracy, I guess you could say this is kind of like Crank-Nicholson, we evaluate f multiple times. So for example, we have the modified Euler, which says yn plus 1 equals yn plus tau of f of tn plus 1/2 tau, yn plus 1/2 of tau f of tn yn. Now you see here we're evaluating f here and here. This is a modified Euler method. And then there is sorry. Apologies. The classical fourth order method, or Runge-Kutta method. Classical fourth order. Okay. Which is a very complex formula, but basically yn plus 1 equals yn plus 1/6 times in parentheses y tilde 1 n plus 2 y tilde 2n plus 2 tilde 3n, sorry, 2 y tilde 3n plus tilde 4n, where y tilde 1 n is equal to f of t and yn, y tilde 2n equals f of tn plus 1/2 tau, yn plus 1/2 tau, y tilde 1n, y tilde 3n equals f of tn plus 1/2 tau, yn plus 1/2 tau, y tilde 2n, and 4n, y tilde 4n equals f of tn plus 1/2 tau, yn plus, you probably guessed it at this point, 1/2 tau, y tilde 3n. Now, you know that when we're doing this one, we have to calculate f of something, and not the same something, 1, 2, 3, 4 times. On the plus side, it is O tau to the 4th, so it does get accurate very fast, but at the cost of calculating f a bunch of times. What's another thing we can do to increase accuracy? Well, instead of calculating f a bunch, we can store the previous approximations in memory and do what are called linear multi-step methods. And basically, as the name implies, they look at multiple time steps as opposed to one-step methods, which only look at one time step. So the basic formula is if k is a positive integer, I guess plus, then we're looking at a formula for sum of j equals 0, alpha j yn plus j equals sum j equals 0 to k beta j yn plus j. Sorry, n plus j. F of tn plus j yn plus j. Tn plus j yn plus j. This is the basic formula. Now we can, if we plug in the right things, we can find a lot of, we can find the previous one-step schemes. For example, if we plug in, let's see, alpha equals, negative 1, 1, and beta equals 1, 0, we find Euler, and for the rest as well. There are two well-named schemes. Notably the Adams-Moulton 3-step and Adams-Bashforth 4-step scheme that both have somewhat complicated formulas, which I suppose I will write here for the sake of completeness. 1 plus 3 minus yn plus 2. This is Adams-Moulton 3-step scheme equals tau over 24 fn minus 5 fn plus 1 plus 19 fn plus 2 plus 9 fn plus 3, where fn is equal to f of tn yn. And Adams-Bashforth 4-step minus yn plus 3 equals, on second line, tau over 24 negative 9 fn plus 37 fn plus 1 minus 59 fn plus 2 plus 55 fn plus 3. Yeah, so those are some example linear multi-step schemes. And then there's the concept of stability, which I'm just really briefly going to cover. But basically the idea that small changes in initial conditions, especially on multi-step schemes, small differences maybe, more accurate, easier to say, and better to say that. Small differences in initial conditions should lead to only small differences in approximations. We do not want raising one of the initial parameters, like, the value of y0 or something, or, the value of the first value of y1 by a very small number to lead to something wildly different as far as the approximation is concerned. And that's about it. Thank you for your attention. I hope you learned something useful.